All right. Thank you everyone for joining. And today we'll have Alex and team from Quantinuum talking about the HPC QC integration. So I'll hand it off to Alex.
Thank you, Amir. On this happy Monday, the 13th, Quantinuum team consisting of me, Alex Chernogozov, Neil Erickson, and John Children will talk a little bit about Quantinuum and our perspective on hybrid. I'm a fellow and a software architect for our complete stack. Neil is leading our on-premise software services, and John is responsible for hybrid workflow application scheduling. So we'll tag team this one and give you our perspective. Starting with a short introduction, describing Quantinuum to people who may not be familiar with us. A little bit about the motivation for why we think hybrid quantum classical is important and some of the challenges. Neil will talk about job submission and scheduler control, and John will round it up with workflow management. And since I don't see the hands, if somebody has questions, you have to interrupt me and tell me. So starting off, Quantinuum is about a 700-person company at this point to work with a number of industrial collaborators across telecom and finance and pharma and automotive and other industries. We focus on cybersecurity, quantum chemistry, or materials discovery in general, or material science more generally. We have efforts in algorithms of quantum algorithms in general, AI and ML applications. So have done some work in natural language, quantum natural language processing. The middleware in the middle of this picture consists of Ticket, our optimizing compiler, and software development suite. It's been recently augmented by a new programming language called Guppy. TIACRISE is our workflow orchestration engine that we'll talk about quite a bit more today about. And Nexus is an integrated platform for users to interact with our system. We have a middleware that's additional middleware designed for simplifying fault-tolerant computing in terms of definition of quantum error correction codes, working with quantum error correction codes with logical qubits decoding, and that sits on top of the Quantinuum systems. We build and-trap quantum computers, and it sits on top of a couple of third-party platforms. We have pretty decent support for IBM still in our platform, and others might be added to it. So that's a very brief introduction about areas where we play. And let's move into why we think hybrid is a good thing to investigate. Hybrid here specifically is talking about high-performance computing and quantum computing. High-performance computing has been used extensively to model nature at macro and even micro scales. It's very good at it. With some approximations, it can do quantum chemistry computations. It can do a lot of material science computations. But there are limits to where you can push classical computing. So this is where quantum computers come into picture. Quantum computers are really good at modeling quantum effects. So there is a belief that combining the two would lead to better, more accurate, faster to compute physical models of nature. We have a paper that demonstrates an example of that. It's a very cool example that shows selective photoisomerization of a retinol embedded in large protein bacteria rhodopsin, where if you shine a light on that Retinal, it changes its configuration from cis to trans selectively based on the environment in which it's embedded. And studying that effect, it's a bit of a textbook in biochemistry. So in this particular case, you distribute the work meaningfully between HPC and quantum. You let the HPC handle a very large protein environment, which would be exceedingly difficult, maybe impossible to model with quantum. And you focus on the reaction center where you have fairly small molecular structure with strong electronic correlation. You give that workload to QPU and interacting those two results in a reasonable workflow and a better solution overall. So that, to me, it serves as one of the key motivations for why it's good to consider HPC and quantum in a hybrid setting. There will always be things at which HPC is better at. It's faster, cheaper, and there's already all the software for handling it, and there will be other things at which quantum is better. And they would typically be at the quantum scale and modeling systems that are not currently possible to model with HPC. So before we go into describe what Quantinuum does, I wanted to touch on some of our core beliefs or principles that we have in place. And the first one is I already touched on HPCs and QPU will be deployed side by side to solve some industrially relevant computational problems. That can happen now, and it will certainly happen in the future. They operate on similar timescales, and those timescales are not your typical coprocessor microsecond level timescales. Meaningful applications on both sides will take seconds to potentially hours to compute. So it's we view it as less of a coprocessor and more of a workflow type situation. And hybrid applications will likely require complex interactions between HPC and QPU as opposed to just HPC prepares a state, quantum computer executes something, and HPC post-processes results. That may be one of the workflows, but we see the need for much more complex interactions between them. Both HPC and QPU are rare and expensive resources, and therefore we want to make the best use of them. Hybrid systems are intrinsically multi-user because they're expensive and rare. And the last one is our operational environment or operational motto is that QPU is self-contained. You don't need an HPC to run a quantum job. If you get a QPU from us, it comes with everything it needs to perform the function of a quantum computer. So with that in mind, let's talk a little bit about what happens when you start putting QPU and HPC together. One of the first things you discovered that you have a bit of a scheduling problem. And the scheduling problem is non-trivial, it's structural. It's structural because if you look at how you scale your HPC, you add your CPUs, GPU cores, you add memory, you add storage, you basically scale out by adding more boxes. If you look at QPU, the scaling is in qubit count, fidelity is execution speed. It's very different, and the way they scale is very different. There are common goals, though. If you try to co-schedule the two, you're trying to optimize resource utilization and trying to maximize the throughput of your job, so you minimize the downtime of both of those rare and expensive resources. You provide some kind of multi-user access to both systems. So while there are common goals, the scheduling properties are very different. So when you schedule an HPC, you typically have quite a lot of scheduling dimensions. You can split your large HPC into boxes, into cores. You can segregate resources by memory. You have a lot of freedom there. When you schedule on a QPU, you have only one scheduling dimension. It's time. there is really nothing else you have to play with, because you're not going to add qubits on a fly. You're not going to, for the foreseeable future, you're not going to split qubits between different users. There's just not that many of them to go around. You know, all of the other things, they kind of come with QPU as you install it. They may improve over time, but it's less likely. So the claim here is you've got just one dimension to play with. So with that in mind, how do you schedule a quantum compute? There are a couple of ways you can go about it. You can do what is probably the simplest approach. You have priority job queues. You designate some number of queues, let's say high, medium, and low. You get all your quantum jobs coming in, and you do first in, first out based on some priority formula that you apply for. Maybe you first drain your high priority queue, then go to medium, then low. Maybe you pick some number of high priority jobs, then allow medium and low to run to give it some level of fairness. That's one commonly used approach. Another approach that Quantinuum uses, and we'll talk about, Neil will describe in more detail, is adaptive queuing, somewhat similar to what was presented earlier in the sessions, where we don't even have a concept of a queue. You have a pool of jobs, and from that pool, you pick the next one to execute just in time, right before the QPU is ready to execute it. And moreover, you don't schedule jobs, because a job may be, let's say, 10,000 shots, and maybe 10,000 shots takes a couple minutes to run, and maybe you want your QPU to be more preemptible, so it allows multiple jobs to run roughly at the same time. So we do this time slicing, which is a fairly common operating system concept, where you time slice your jobs, and based on some formula for picking the next one out of this pool of jobs, you execute a slice, and then you re-execute that fairness algorithm to pick the next one to run. So that may be another way of scheduling quantum jobs, given that time is the only variable you have to play with. Neil will talk about it in more detail. So coming back to the how do we co-schedule, you have the hybrid job, and that needs both HPC and QPU resources, and both are rare and expensive. If you take an HPC-centric viewpoint, whenever I have a hybrid job and there is a time to do something quantum, I want that quantum computer to be available right away, because I'm the big dog. I'm a multi-million-dollar resource sitting in a national facility. QPU is a little thing on the side that needs to be available whenever I ask for it. And that's, let's call it a big dog syndrome. The QPU-centric viewpoint is a little bit different. So QPU is an aspiring big dog. It knows that it will be doing something really important in the future, and it understands that, yeah, I only have time to play with, so I need to process jobs from multiple users. Not all of those jobs are coming from an HPC cluster. These two are somewhat in conflict. So how do we deal with it? We suggest that maybe there is a way that we can work with both of them, use their strength, and don't try to fit one into another where they're really incompatible. Don't try to make them compatible by artificially creating commonality where there is none. So our approach here is to rely on a hybrid workflow system, which does not try to replace any of the existing schedulers. It's not trying to replace HPC scheduler with something QPU away. It's not trying to make QPU into an HPC scheduler. It just works with both of them side by side. and both HPC and QPU resources are allocated whenever there is a need for them. And the way it's done is by coordinating your hybrid application, which can be described as some form of workflow graph where you have some classical computation, you have some quantum computations, you have some more classical computation, and this graph is what determines where the computation is performed. So the workflow scheduler is then responsible for a relatively simple task. When it sees a classical computation, it sends it off to an HPC cluster. When it lets HPC schedule and take care of it. When it sees a quantum computation, it can send it to QPU and let QPU schedule and deal with it. And whenever the data for the next one is available, that's what triggers the computation. So to make the system performant, you need to assure a couple of things. You need to make sure that quantum and classical tasks, multiple of them, can run concurrently, and that data dependency trigger the handoff between the tasks. There could be multiple classical tasks, and they hand off based on data availability for the next task. There could be classical to quantum. So this quantum task starts executing whenever a classical input for it is available. And this classical job starts executing whenever the output of a quantum job is available for it. So that's the viewpoint that we will refine in the presentations by Neil and John following me. So I'll take a really quick pause before we move to job submission that Neil will cover. If there are no immediate questions, then we'll go to Neil and we'll open it for questions at the end. Go ahead, Neil.
Okay, great. Yeah, thank you. Thanks, Alex, for the intro. So we're going to talk a little bit about some of the specifics of how we have an entry point between our workflow engine and our QPU that we've deployed on site. So to just explain the need for a direct access API, given that in these situations where they've purchased a QPU, they have a HPC and a QPU near each other, we wouldn't want to force access between those to go through cloud APIs such as Quantinuum Nexus. That just adds latency and network overhead. It makes it vulnerable to Nexus outages, which of course happen occasionally. Even cloud provider outages like Amazon and other clouds go down, and you certainly don't want your QPU to not be functional for hybrid execution because of some generative AI mistake at AWS Web Services. Additionally, this API being purpose-built gives us the opportunity to make the shape of the API optimized just for this use case. So the way our APIs are built in our cloud offerings are definitely towards like a different, more flexible and more complicated set of use cases. For hybrid, we have like a more focused API that just delivers what's needed for those needs rather than any other kind of complexity. Alex, thanks. Here's a simple diagram to just demonstrate what I meant. To be clear, the green rounded box for the on-site deployment is referring to our QPU as well as the surrounding control systems and other software layers. And all of this is located in the same area. And here you can see that some kind of RPC client on the HPC, which is represented by of course, the picture of the box, server boxes there. It's able to directly submit RPC methods to what we call the QSubmit API, and it's able to receive results and metadata and other types of operations. And that API is a front into our actual Kubernetes cluster of processing services and data stores. And that then integrates into like our normal scheduling and execution flows down to the QPU, where it's run just normally, where the QPU has no knowledge that it's special. Next slide, please. Some details about this API. We mentioned it in the previous slide, but we've chosen gRPC for our our RPC backbone, and we've written the rest in Go, of course, to make it convenient. It's hosted in the on-premises Kubernetes cluster, which is nearby the control system hardware, as in the diagram. That Kubernetes cluster is, as mentioned, kind of like the on-prem offering that always is delivered with a Quantinuum quantum computer on site. For simple but secure authentication, we use an MTLS approach, where we distribute the server certificates to the integration workflow points in the hybrid compute environment. And the API that we provide has straightforward job submission and execution methods, which can be as simple as given this job, I'll just wait for the results and get them streamed back to me. We also have features such as an ahead of time compilation with a intentional triggered execution workflow in the case where the compilation is taking longer than we want to wait live for that sort of thing. And we also support, in terms of getting results back from the quantum computer to the HPC, both streaming continuous result methods, and we also have, of course, just standard kind of like synchronous results fetching, which can be done real time or afterwards to fetch historical results. And yeah, currently actively used in Japan at the Riken site. Just a little more detail on our choice of gRPC. We chose it because it's used extensively in the industry with a lot of good tooling and multi-language support. The really nice thing there is it allows generation of client code in numerous languages, most notably like Python and C++ being the things that would be relevant to a scientific computing environment, which allows us to not have to write everything in C++ or something, but allow whatever HPC languages are needed to be able to communicate with this without us having to build our own client and spend a lot of effort on that. It has like a very straightforward way of defining your service definitions that's easily turned into documentation and provided to the client. And it supports both, as you can see in the diagram on the right, request response RPCs, as well as server-side streaming that we use over the HTTP2 protocol, which allows a single request to result in a series of responses from the server. And that's how we would deliver an end-to-end execution of a job, where the request would be a submission and the responses delivered from the QPU server to the client are the results messages, and then eventually a message indicating the completion. And gRPC, of course, uses protobuf in terms of its message passing, which is very compact and is flexible enough for schema evolution and versioning to allow us to make changes and be confident that we aren't breaking anything, as well as integrating, of course, with the service definition, all being part of protobuf. It's very convenient for both code writing and documentation. So here is a UML sequence diagram. As you all know, I'm a proponent of those. Just showing a simple submission workflow where the RPC client, living on a part of the HPC, submits this job, and then QSubmit receives it. In step 2, does the compilation, which is to take that job and make it able to be executed on our QPU. And then as that job gets ready, it's passed to the QPU through the scheduling algorithm mentioned before. And then as the QPU processes those and streams results upward, we restream those back to the that original execute RPC invocation until eventually the job is complete, and then we close that result stream. So that's kind of like our happy path for that execution. Now, now that we've talked a little bit about the front door, we'll talk a little bit about what Alex mentioned in terms of adaptive fair queuing and time slicing. So for our scheduling needs, this, as Alex said, this is an intrinsically multi-user scenario. These QPUs are expensive and they want to use it in a variety of different ways. So our hybrid execution jobs, as they come in, they need to take priority over standard jobs. And what I mean by standard is a non-hybrid, a just QPU job. So just some chasm that needs to be executed and then returned or the like. We want to minimize. The reason we give those priority is because during hybrid execution, both the HPC and QP are kind of being committed to this. So we want to make sure we're not wasting time doing something else when we could switch to something that's a higher priority. Um, Now, the nice thing is that we have an adaptive fair queuing system that we've built not originally for this, but it has enough flexibility to accommodate this use case. So we're basically leveraging our existing scheduling capabilities for the QPU rather than trying to build something else that would be more complicated. Um, there are some customization points to how this scheduling extensions work. So we work with the on-site deployment to make sure it's going to behave as the customer wants it to. And again, the goal is to minimize the wasted, quote unquote, wasted time. We want to make sure that both HPC and QPU are running as much as they can because they're expensive and precious systems. So here's a very simple diagram to demonstrate that. Of course, we have our HPC users, and they're making RPC calls to QSubmit, as we mentioned, while we have other users who may belong to the same organization as the HPC in the grand scheme of things, but they may be submitting standard quantum jobs simply through Quantinuum Nexus, doing whatever kind of research they want to. So our scheduler accommodates both submissions from Nexus and submissions via QSubmit and is able to interleave correctly and optimize for the outcomes that we want. Given that being that HPC jobs run in a higher priority class, so that we don't waste that time. Here, I'll talk through a little bit about our fair queuing algorithm. I won't go into this a lot because it ends up being a bit fractal, and the closer you look, the more complicated it gets. And there are a few other levers that we have in play here, but in a simple way to view it, as a QPU is ready to execute work, it sees it has it observes the organization and basically says who deserves the time right now, who has done the least in our overall window of time. And then given within that org, it selects based on internal priorities, which of the work inside that org should be done, which ends up being roughly FIFO with some complexity around priorities. And then it executes what we call one slice of that selected job, which is generally a couple of minutes, depending on the size of the job, but at most a couple of minutes. And then the outcome of that job being executed changes the state of the system via what we call accumulation. So we record that organization had work executed, and then we repeat this cycle. So we're just continuously going to go through, meaning that as you can see, jobs kind of end up interleaved and split up during the QPU time, but it allows us to keep, for instance, organization one from simply dominating the single QPU during that entire time window. So the other thing that other notes is that we have this fixed window of a certain amount of time, and then we reset it to kind of like adjust things to keep it relatively even. And we also use a thing called this fair queuing multiplier, which means we can reward or punish orgs. And there's a lot of reasons why that happens, but it allows us to put our thumb on the scale when necessary and keep everything overall even. So as mentioned, QSubmit integrates with this existing fair queuing scheduling, so it submits jobs with certain giving priorities, and itself has its own high and low option. And so this enables us to interrupt less urgent work in favor of hybrid execution jobs. Note that when I say interrupted, I do not mean that anything is lost or wasted. As mentioned, we have these slices that we're running. So at the end of a slice is when we would reevaluate what time. So a hybrid job will not interrupt during the execution of a slice, but it will take over at the slice boundary for the QPU. So here's an example specifically for this hybrid situation. we have job one, and I've notated this as job one : slice one, just for this example. But here you can see we have some orgs that are just doing work, normal standard work. And then in Coral, we have this hybrid job comes in. You'll notice I put in some arrows for kind of a blank area. That's to indicate that there's a little bit of a lag when the hybrid qsubmit job comes in, as it's compiled and ready for execution. Once it's actually ready, it interrupts the execution of the other orgs and continues to result stream out. And then at the point which that's completed, we've kind of adjusted everything back, and now the work for the other orgs and users will continue to execute kind of as it was before that hybrid job interrupted. Thanks.
Hello, I'm introducing myself now. I'm John Children, and I am working in the hybrid compute part of Quantinuum. I'm going to talk to you a little bit about what we're thinking about for workflow orchestration, workflow management system Tierkreis that I will introduce as one of our primary approach to this problem, and a little bit about the decisions we've made in that area. So next slide, please. Thank you. So elephant in the room, why we're doing something new. And this is really born out of our experience in this area, and this workflow management system has been developed over a number of years at Quantinuum. So we found that when we've looked on a survey of different workflow management systems, we didn't find one that suited our needs for this hybrid HPC problem. And I've got a few of the reasons why here, as not an exhaustive list, of course, but usually HPC and quantum integration is an afterthought in a workflow management system. You have your workflow management system for ETL pipelines or something similar, machine learning, and then somebody's tacked some quantum stuff on top. And often these workflow management systems don't support some of the things that we need for like a variational workflow. So it was difficult to find ones that had like loops and control flow at higher order. As sort of mentioned with the ETL kind of ones, they're often very data science and Python focused, which is not really representative of the kinds of efficiencies that we would like in HPC. So they kind of assume that you're going to take a Python function, pickle it, and send it to some compute node, which then if you have a Python version mismatch, is not really desirable. Making it so that we can have something that's a bit more cross-language, it would be beneficial in that area. And of course, the programming interface can be a bit unwieldy. So often you're writing like YAML files or something similar, and then if you get like the types of one node wrong compared to another, you then have to rerun the whole workflow or try and repair it. And obviously, GPU time and HPC time is expensive, and we don't want to have to be like checking on the workflow, editing and stuff. So having something like type checker or a way to really debug and develop your workflow in a nice way is beneficial, we found. So, and visibility is also quite important there. And when you're in the HPC environment, being able to actually visualize your workflow from the login node is very beneficial. Sorry, next slide, please. So with these things in mind, and as I mentioned, we've been working on this new hybrid workflow management system. What are our design principles? So although I said we're building something new, we also want to integrate as much with the existing systems as possible. We want to reuse all your existing MPI programs. We want to reuse your like HPC schedulers. We want workload managers. We want to be able to reuse the various tooling that you already have. We also want to minimize the idle time, which is a little dog analogy that Alex had earlier. So we want to make sure that we're not leaving a HPC node running while we wait for quantum resources to finish. And we don't want to like reserve it for a worker that we don't have work for yet. And we also don't want to have the QPU sitting idle either. So we don't want to reserve it if we don't have stuff for it to do. So that's where the sort of workflow system comes in. We want to have a friendly programming interface. So make it nice and like literate and make it not very error prone, hopefully. And then we want to support things like control, flow, and loops in our workloads, and give you tools to look at your workflow as it runs and see what it's doing and debug it if needed. So next slide, please. With this in mind, I've introduced a little bit about the TFRS programming model. So it's a DAG, and we've got a sort of screen grab of part of the visualizer, which it's a sort of interactive browser-based thing that you can zoom in, and we'll talk a bit about it later. But effectively, we just have a big computation graph that's made of nodes, and each of those have edges that plug into other nodes and data passes along those nodes. I'll talk a little bit about how that happens later. But because we have this partial ordering of data dependency, we can execute different parts of the workflow graph in parallel, depending on what the data dependencies are. So this lets us do parallel asynchronous execution. We can kick something off to the QPU or kick something off to some compute nodes and just wait for them to finish. And we've also added some extra features on top of that. So you can see there's a map node and there's an eval node, which lets us do computations in parallel. And eval is sort of like your list style eval, but with graphs. Next slide, please. So that was a little view of the visualizer when it was complete. This is what it would look like when things are running I mentioned the debugging and usability. So we have a color coding, and this will update live with a WebSocket if you've tunneled into your login node. So you can see when nodes are complete. So I've got some constant nodes that have passed in some values, and then there's a node that's currently running, and then some nodes that are white and they're waiting for computations to complete. If you have an error, it will go red, and you can look at the logs for that node, which is all sort of plugged into your regular standard Unix tooling. Next slide, please. And I also want to show a little bit about how the higher orderness works. So you see we've got this map node. And there's a plus sign on it. And if we go to the next slide, we can see how that expands. And you can do this sort of progressive disclosure in your higher order workflow to go down into each node that's higher order and see how things are running, and also after they've run, debug them as they've done. And you can sort of open and close stuff, and you're not overloaded with information right at the start. Next slide, please. So a little bit about the execution model, how this works. And I would love to explain this in more detail if anyone wants to follow up afterwards. But we have a process that runs on the login node, and that looks at the graph execution state from the file system. And there's a few different arrows going on here. But using the workflow that users have built, we dispatch stuff to the kernel as like a subprocess, or if it's something a bit more heavy duty, you need MPI for it, or just like a larger node. You can submit it to a compute node using like PDS or Slurm or PJSub, like the Fujitsu scheduler. And we just dispatch things to existing tooling. And then all of the interactions are mediated by the file system. So those workers that I'll talk about a little bit more in a moment will read their inputs from the file system and use the distributed file system from the HPC center. And it will then do the computation it needs to do and write to the file system. So we don't need to load the files at any point into the login node itself. We can just have one worker pass its inputs to another worker, which is obviously more suitable to HPC environment. And you can also have, if you need to do add some numbers together, do some conditional logic, you can also just have stuff run on the login node and not have to wait for the queue, which is very nice. Okay, and indeed, we have workers for interacting with the QPU itself. So the stuff that Neil has introduced about using QSubnet, we have workers that will send jobs off to the QPU and then pull them back and then write the outputs to the file system so that they can then integrate with the whole workflow system. Next slide, please. So when I mentioned about these workers, so we publish a few different prepackaged workers, and Tierkreis is an open source project. You can go to Quantinuum Tierkreis and take a look. We've got a few for like PyTicket and for some of our other software. We also have a few different built-ins, like adding numbers together, doing conditionals, list operations, this kind of stuff. But you can also write your own, and it's very easy to do with a Python function. But you can also like, and we did things like take ntchem, just the binary, and wrapped it and made that into a worker so that we could run it in an MPI thing to do our chemistry calculations. Or you can wrap a sort of regular bash script or a general binary, and there's a worker protocol which you can implement. And I've implemented it before in Rust as well, so I've had a Rust worker and run that on a compute node as well. So the workers also have type signatures, and this is sort of gradual typing to some degree because we realize that like adding a type signature to your Unix command may be slightly undesirable. But workers who are implementing Python will automatically get type signatures, and we will check that those will match when we build the graph. So we can have this sort of language agnostic thing with gradual typing in a Python SDK. And obviously, if you go and look at our documentation, there's a lot more detail about that there, but I won't go over that right now. Next slide, please. So checkpointing as well. I mentioned that the file system is the medium by which workers communicate and the way that we check the state of the execution. But this also has a secondary advantage in that we have checkpoints for the execution. If something goes wrong, we can resume from those checkpoints, and we can look at the logs or the inputs to each node, and we can restore and we can restart the workflow from different points. So we can choose some nodes in the workflow and have them redone, which is nice if you've made a mistake in one of your workers and you want to edit it and then restart the computation. So if you've done some expensive QQ calculation, you can sort of edit your workflow and then resume from the point after you did the processing that failed, which is something that we found quite useful. Next slide, please. And I've mentioned that we dispatch to the schedulers. So we have this, and many different workflow managers have this, a sort of abstraction for execution, but we've gone through and we've made sure that we've actually tested and implemented executors for Slurm, Fujitsu. PBS is a little bit less tested, but we've certainly used the Fujitsu one for a real experiment, and we've tested Slurm reasonably well. To take a sort of higher level description of the resources that you need for your worker tasks and produce batch scripts just through templating and submit the tasks that you need for those things. And those things are bundled into the main Tierkreis package, which, as I mentioned, is open source, and you can find it on GitHub. But yeah, it allows users to then say which of the tasks in the node need which resources, and then we will make sure that those resources are put into the script that we use to then run that worker. And I think that concludes my presentation, but I think we have some time for questions. Thank you. Back to Alex, I think.
Okay, so I would like to close it out just by saying that hopefully that gives the audience a really quick overview of the approach we've taken, which is QPU and HPC operating side by side, coordinated with the workflow scheduler and utilizing high performance communication protocol between HPC and QPU while making the best use of existing tools, not reinventing the schedulers that were created for HPC or QPU, just maybe living off the land in HPC and QPU space. So with that, thank you, and we're open for questions.
Thanks, Alex. I'll actually start with one, and then we'll open it up to everyone else. But so when we talked at the very beginning, we're talking the core beliefs was that QPU self-contained. I'm wondering what's the deployment model there, and what's the role of HPC? Like do you just support, you give everything to an entire QPU, which includes some HPC clusters that are used for classical purposes, maybe compiling, maybe the scheduling, and maybe other things, error correction, for example. But who's going to maintain this HPC cluster? How does it fit within the HPC ecosystem? Is it completely something that's owned by the Quantinuum and nobody else touches it, or is there some collaboration going on there?
So if you specifically zoom into quantum error correction, the QPU will contain all the pieces to run fault tolerantly, including decoders, compilers, everything else you need to do. So we don't think of it as HPC proper. We think of it as part of the QPU. When you say you buy a QPU that can fault tolerantly execute some algorithms, that QPU has everything it needs to execute those algorithms. And if you buy it from Quantinuum, Quantinuum is responsible for making sure it does what it's supposed to do. That does not mean that it's self-contained to the point where you can't make it work with HPC. Hopefully this presentation shows you that it can work with HPC, but it works with HPC more at application level as opposed to inside the quantum computer. Inside quantum computer, there may be fairly significant classical resources, CPUs, GPUs, FPGAs, whatever they might be, but with best way to think of them, the black box, the part of the QPU.
Sounds good, thank you. Orlene, I think you're next.
Yes, it was actually a related question. So the scheduler and the QSubmit server, do you operate them? Or do you expect the HPC center to operate the infrastructure on which they are deployed? It was part of Neil's presentation.
Neil, you want to take that one? Well, I'm trying to find a slide that may be good.
Yeah, I think if I think I understood your question, it's two different teams working in concert are kind of responsible here. So in terms of what's in the green, the teal box here, that's entirely the quantum stuff, which was like basically Quantinuum is responsible for everything within that. So we actually have like employees executing on site, managing the quantum computer, et cetera. And then the HPC side is run with the responsibility being that customer. But of course, there's like a deep integration where people like John Children would be helping them to implement the Tierkreis interaction and that stuff. Did that answer your question?
Yes, absolutely. And so a follow-up question is the fair share mechanism that you presented is part of the probably somewhere between the QPU and the QSubmit API, so probably a microservice, I suppose.
Exactly. Yeah. It ends up being a couple of them. Yeah.
Can it be configured by an administrator, for instance, of the HPC center, or is it only configured by Quantinuum people at the moment?
We configure it, but we work with the HPC side to see what they want, how they want that interruption behavior to be configured as. So it's hard coded in some sense, but it's hard coded with an agreement between the two companies.
So there is maybe a slight clarification here. It really depends on HPC operator.
Yep.
We're offered to provide a schedule and control service, for example, to Riken, so that all the fair queuing parameters could be adjusted in real time as it applies to the HPC. It just haven't been implemented because there was no need. That environment is not as dynamic or flexible, but in theory, you can control the quantum scheduler from HPC side. to the extent that whatever is owned by the HPC could be configured and controlled. If that QPU is also used by other users, maybe other HPC or direct users, then the HPC shown here on the left would be limited in its management to just to the resources it owns, not to other resources that are managed by other organizations.
It's clear. Thank you.
Santiago, I think you're next.
Thank you for the presentation. I have one quick comment and one question. On the comment, I really appreciate the use of gRPC as a client. When we talk to our cybersecurity people inside a legacy NSF funded center, security is pretty important, and this is becoming much more significant for Quantum than we even imagined on our side of developing a similar effort at a much smaller scale. Now, the actual question is, for specifically NSF funded centers that operate by giving people allocations, there is special interest in understanding how scheduling ties to a cost model, specifically when you have a fixed allocation for users. Can you elaborate a bit on how you're thinking along these lines?
Neil, you want to take it, or you want me to explain?
Why don't you take it, Alex? Yeah.
So in the quantum system, there is organizational constructs that along the lines of organization, group, user, there are other levels you can model the data, and there could be quotas and usage associated with each level of that hierarchy. That is all exposed to the HPC. HPC can both read and configure the quotas and read the actual usage against the quotas.
Okay, thank you very much.
That answers your question.
Yes, I'm trying to think about how the choice of having this hybrid scheduler where queues are not exactly there is I think it is very interesting. It just made me think about how that would change the perception between managers of a site and people who are users of the site in terms of the make span of their tasks, for example.
Yes, so maybe one way to think about it, as a user, you see the progression of your own jobs, and they always go pretty much in FIFO order. So whatever you submitted will be executed and QPU in a FIFO order, unless an admin changes your priority along the way. So that could allow you to jump the queue. As an admin, you see multiple users within your organization, and you can split them into groups. You can assign different priorities to groups, maybe by project that they're working on, things like that. So you have a lot more flexibility, and you have broader view. But again, you have visibility into how much work each individual user performed, how much work a particular group has performed, and you can aggregate the data and display it in a way like it's available through an API.
Thank you so much.
Yogesh, go ahead.
Sure, thanks, Alex. Great, very helpful presentation. I wanted to drill down more on the time slicing of the QPUs, right? So four quick questions. So one, how common is this time slicing across hardware providers? Is it something unique to Quantinuum? So what's the time granularity at which you're slicing? Is it microseconds, milliseconds, seconds? And what's the context switching overhead that you sort of suffer as a consequence of that? And lastly, what's the impact on noise and error correction as you slice the shots across multiple time slices?
That's a big question, but I'll try to unwrap it maybe a little bit. So time slicing is a very common classical operating system concept. Most real-time operating systems, they use time slicing. So it's you basically allow any given task to use CPU for X number of milliseconds before you have to reschedule and reevaluate your schedule. So we haven't invented any new concept here. We just applied it to quantum. The way we applied it to quantum is we realized that most jobs have a number of shots for statistics. So the quanta here is a shot. So you can have time slice per shot and a number of shots. On our system, we calibrate between slices, or there is an opportunity to calibrate between slices. So calibration can be viewed as an interrupt. It's an interrupt in a sense that whenever a slice finished executing, there is an opportunity to run calibration. And that opportunity is evaluated by the system, and calibration is either run or not, depending on the parameters that we monitor. About the overhead, there is obviously some tasks switching overhead, but the overhead here is unavoidable because of the calibration requirement. We're required to maintain our published fidelities at all time, and therefore we need to reevaluate calibrations fairly frequently between job slices. So the additional overhead of scheduling and doing some fairness is negligible because we already have to do that. You guys, did I cover all the topics or did I miss?
Yes, we did. It could be a long answer, but this is good enough for now. Yeah.
Right.
Thomas, go ahead.
Yeah, I really enjoyed the talk. Thank you. I had a question about the workflow system at the end. I noticed you guys were using the file system for sharing between jobs, and I was curious if you've run into any problems with that, and if you considered maybe message queues or any of those things as an alternate to a file system.
Sure. Thanks for the question. Yeah, it's something that's in active development to some degree. We've had so this is the second version of Tierkreis, and the first version was actually gRPC based in the interaction. We found that for the amount of data that we had for some of the experiments we were running, the file system was enough. I mean, you only have small amounts of data that you actually load into the QPU anyway. And do big computations, small data is something that one of my colleagues is fond of saying. I am very keen on doing stuff with message queues in general. We're looking at doing like a sort of cloudy version of Tierkreis at some point potentially, and that would also be message driven. So it's, if you look at the Tierkreis open source repo, you can see where I'm working on things a bit. But yeah, anyway, sorry. Hopefully that's a little bit of an answer, but maybe not exactly everything.
Okay, thank you.
Yuri?
Hey, thank you for the talk. It's great to see the parallels in your technology choices, Kubernetes, TLS, gRPC, and what you do, as well as sort of the approach to cover scheduling. But my question is about sort of the overhead, if you will, or time needed to schedule the slice, right? So I'm assuming slice is a collection of, it's a circuit, it's a collection of shouts, one or more, as Alex described. But you know, compilation optimization takes some time and context switches. So could you describe some more? Is there any sort of effort to reduce that overhead that is, you know, associated with each management of a slice, right?
I can.
Let me do it real quick, and if I don't cover it. The overhead is actually only associated with the job. We don't do any recompilation or anything with the slice. All the calibration data is linked into the executable, and then the overhead for that is some millisecond.
Okay, so basically understand, job is a it's a circuit, has a number of jobs. It includes pieces that are HPC as well as QPU bound, and you kind of pay the overhead upfront for the job scheduling at that granularity, and slices are really just sort of the slicing, if you will, of the QPU time in a sense, right?
Yep.
But okay, all right, and that explains a lot. You know, I think I better understand those pieces. All right, thank you. I think we are out of time. Yeah.
you guys have time for one more questions, or do you have a dead stop at the top of the hour?
Good time.
Okay. So back to the time slicing. Have you guys given any consideration to the idea of quality of service? And particularly, you said that you, for example, prioritize the hybrid execution model, which is sort of similar to what JHPC has done in Japan, but they did their own implementation, I believe, above above Quantinuum. So when we'll stop there. Is there any cost consideration? Like, do you have, when you consider, I'm going to execute this job, do you give any guarantees that this job will complete within a specific amount of time if there's some other resource waiting for it?
I think the best answer here is it's negotiable. It's really when we install a QPU at HPC side, that's where we have this conversation. What makes sense for that HPC provider? What are the ways to use QPU they have while it's deployed on their site? So it's these are the discussions that can happen when the QPU is deployed. There is a lot of flexibility on both quality of service and configuration. It can be changed at any time, but typically we're trying to do it upfront. So it's once it's deployed and provisioned for operation, it's clear how it's going to operate. So with Riken, we had a set of conversations, for example, for how to operate it with Fugaku, and they had a certain vision for how that system wants to operate. We just configured it to operate that way. If we install it somewhere else, it will be a similar conversation and similar customization. It's side-by-side operator-by-operator customization.
Sounds good. And the other thing, when like it seems Quantinuum is focused primarily on the workflow model where you have the separate steps of classical and quantum. So in that context, what do you consider hybrid execution? Because everything is not hybrid now, like quote unquote not hybrid, as there's no HPC waiting for it, right?
So the overall workflow is what we consider to be hybrid because it contains quantum and classical pieces. Each individual piece, if you're running something on a classical computer, it's obviously classical. You're running something on quantum, it's mostly quantum with some classical compute that's required in support of the quantum program execution. So there is a notion of hybrid while doing quantum. So quantum error correction is typically brought up as a hybrid application. For us, it's easier to think of it as quantum. Yes, it makes callouts to classical hardware. It makes decoder calls. It does some classical logic while the program is executed on a QPU, but it's still a quantum program. And real hybrid comes into play at the application level, where you have an application that you model part of your molecule on HPC, and you model maybe reaction center on a QPU, and stitching those things together. That's what makes it hybrid for us.
So from that perspective, when you prioritize a hybrid application, that means it's working within the trickery workflow, for example.
Yeah.
Okay. And then other like independent submissions going through the Nexus, I believe, is something different.
Yeah. So if somebody is just running quantum programs, so they're not part of HPC workflow, they're not part of hybrid HPC workflow, we typically give them lower priority. But again, it's a policy. By policy, we can configure it any way we like, but to avoid holding HPC jobs are usually considered more important because, again, they utilize two expensive resources, except instead of just one expensive resource. So we typically give them priority.
Yeah. Okay. Do you guys have time for one more or a couple more questions?
Yeah, we can stay as long as you like.
So you guys talked about gRPC. So I have two questions along gRPC. gRPC, does it allow you to have any back-end customization. For example, right now, due to the bandwidth required, Ethernet is fine. But like if you deploy in different systems where they use multiple different types of interconnects, like Slingshot or Mellanox or whatever, is gRPC flexible to be able to support the different multiple backends, or do we need to do some extra work there?
I believe that, and I'm not unfortunately familiar with Slingshot or what you mentioned, but I believe gRPC is always built on like a communication backplane of HTTP2. So I think if that's what you're asking, then that's kind of just like a limitation of the technology. So it'll always be coming through that way.
Okay.
If I may, Amir, right? So it's basically layer 7, right, and 6 at best, right? What is the lower layer, right? So basically, assuming IP networking, right, then then you are fine. But there's ways to do IP over things like RDMA or other user level networking that you described, right? Obviously, if it's something esoteric, but I think as long as we sort of have the model of the layer 4 and above, I think that's fine, and I think that's kind of the choice that we also made. But IP networks or Ethernet-based networks, if you go to layer 3, is the predominant choice in data centers. But you could do something else and potentially reap the benefits. But again, that's sort of a layer 3, layer 4, maybe layer 2 even, kind of a thing. But again, IP will save us, and everything else above that will be, buildable, cascadable up to HTTP2 and the gRPC as a protocol on top of that.
Fair. I guess my question comes from the execution, like with openMPI or other types of frameworks where they're built on top of other libraries like libfabric, and libfabric allows you to have different implementations or different provider plugins for each of the different types of interfaces that can provide different feature set. For example, you can have Mellanox or Slingshot can have, I don't know, tag matching. I don't know if the tag matching matters in this case, but like built-in tag matching versus software tag matching. So there is this ability to build it on top of a library that abstracts away the hardware. And I don't know if gRPC actually does that or not. I'm not very familiar with it.
We can look into this, but I think Yuri addressed that maybe quite well. It's a layer 7 protocol, so as long as you can plug in different network layer, it should work. But slightly different answer, maybe typically, so gRPC in our case is used in a workflow environment, and workflow is rarely executed from a compute node. You can do that, but it also doesn't really make a lot of sense, because that means your compute node is already reserved and you lose the ability of dynamic scheduling of HPC resources. So we would normally run gRPC client on a workflow orchestrator box, which may be a login node or maybe some dedicated piece of hardware on HPC that is doing just that. And then compute nodes is where you mostly have MPI with all the interesting fabrics and all that. But to get from login node to compute nodes, we assume in most cases you would have some kind of IP network where gRPC would be just fine.
Yeah, that makes sense. Sounds good. I think that's all I had. Anybody else have any questions?
Yeah, so if you have time, right? So kind of wanted to talk a bit more about the sort of the part that John described, about sort of the checkpointing and restartability or continuation, right? So what model do you assume, right? So is it sort of like a checkpointing 101, where you capture the state, or and if some aspect of the flow, HPC node or part of the task has failed, you can restart that, or what kind of granularity do you look at? And is there anything specific about quantum or QPU, or the fact that how do you checkpoint a quantum computation other than kind of getting the results from a slice in your terminology?
Sure. Yeah, so the checkpointing is reasonably naive. We do the minimal thing, which is the inputs to the computation and like the configuration, and the outputs to the computation are all that we save. We don't do anything like saving the process state or anything like that midway through. So it does work for both because we're sending it to QSubmit or whatever, and that has inputs and outputs as well.
It's actually, it stems from the data flow model where computation is defined by inputs and outputs, and processing nodes can be viewed as pure functions. So if you have the same inputs, you will always get the same outputs. That's kind of...
Understood. And I think that this is great, as a sort of a being able to restart or continue a computation, especially in the hybrid model where some schedule, some sort of a federated HPC system has its own way of doing things, and may be available, and a equally federated QPU system through your sort of a direct API access also has occasional, like all systems, occasionally is unavailable or fails in producing, right? So that, and kind of a Amir, one last sort of a comment on your sort of a previous question about quality of service. I think, as we think about the openQSE or sort of our microarchitecture, right? I think figuring out what is desirable and kind of the fair share scheduling and the best effort has proven to be quite useful, powerful. I think we have seen examples here, in our talk, and kind of they are building blocks that allow us to reason about some, SLAs or meeting some SLAs. I think exactly how it is and how, on-prem operators decide to slice and dice the time into slices, as terminology here, or something else. That's always allowable, right? But I think the fair share scheduling kind of and the short-term prioritization or the long-term fairness is achievable, and so that seems to be kind of like a emerging good enough technology that sort of seems to meet that. But obviously how it's operated and how it's defined, and how do you do admission of something that for the next month someone has a contract for X many of CPU or QPU minutes, hours, days, that's a more admission as opposed to scheduling and orchestration time. But to be continued, this is just...
Yeah, and to throw one thing out there, maybe because it seems like the fair share slicing and scheduling and time slicing and scheduling that was talked about has been already implemented at JHPC at a higher level. So it seems to indicate that maybe, I don't know what your thoughts about on that. What if we decouple that from the actual, hardware? Do you see any hardware specific requirements that needs that scheduling to work close to the hardware, or can this be decoupled and moved a little bit higher in the software stack?
That's a good question. So in a way, there is nothing specific about it to the hardware. It's fairly generic conceptually. Only one requirement that it needs to be low latency access on demand whenever QPU needs to make a decision. So when you swap in from one slice to another, it needs to be quick. So if you're making a call to an HPC somewhere and HPC takes a minute, now your preemption time is terrible. If it takes a millisecond, that's fine. It can be anywhere. So but it also goes back to if QPU is self-contained, the scheduling, it needs to come in with its own schedule. If it's not self-contained, if you start unbundling it, then there are options, but we need to understand what we're doing with unbundling the QPU now.
Yeah,
makes sense.
And I think sort of thinking from first principles, right, is as opposed to where's the best implementation, right? How close to the hardware or how far away from it is more of defining a meaningful value for the slice, right? So Linux has 10 milliseconds as the default thing for desktop. Is it good? Is it bad? Doesn't matter. Embedded Linux has a very different time slice versus something else. But I think thinking about what is reasonable, right? And hence the questions about what's the overhead, my question about when do you compile and when do you recompile, when you those kind of are the things that drive what is the slice. But thinking of sort of slicing things in something that I would say is not a millisecond, not 10 milliseconds, right? Because there's overhead still in sort of setting up the computer is kind of a first thing, and then slicing things and combining slices and doing sort of a prioritization with some number of slices is probably a sort of a good start to sort of think about that, and less about who makes the decision? Is it something in the cloud? Is it something that's on premises? How close is it to the actual hardware, and that actually controls ions in whatever fashion is the device specificity, right? But anyway, thank you guys. This was very informative.
If there are no questions, thank you, Alex and team.
Thank you all for sticking around over time.
Thank you. Take care.
Cheers.